Okay, so in this live video, we're going to get back to basics and talk about the properties of air. I'm going to use some props here to demonstrate the difference between dry bulb, wet bulb, relative humidity, and dew point. So if you're interested in those things, give this a few minutes and listen on. And if you're in the HVAC business, whether you're a technician or a contractor or an engineer, understanding the difference of the properties of air is extremely important. Okay, that's why we do a lot of these videos. So let's start with dry bulb, the easiest one. So the dry bulb temperature of the air. The dry bulb in here, in my office, we're in Marshall, North Carolina, and it's a lovely rainy day up here, but it's very nice temperature-wise. So the temperature in my office is about 72 degrees. That's the dry bulb temperature. So what does dry bulb temperature mean? And then we'll look at what wet bulb temperature is. So best way to explain dry bulb temperature is with a good old-fashioned dry bulb thermometer, which I bought at the hardware store across the river here in Marshall, North Carolina. Okay, so dry bulb comes from this. So if you look at the back of a thermometer, this particular thermometer is just a plastic one. You see the bottom, there's a bulb. And in that bulb is the fluid that expands and contracts with heat and gives us the dry bulb temperature of the room. The heat that affects this is what we call sensible heat, which we'll talk about in a minute. It has nothing to do with the moisture in the air, okay? The bulb is dry, so it's dry bulb temperature as opposed to wet bulb, which has a wet sock on it, which we'll talk about in a minute. Okay, so the dry bulb temperature is the temperature you see on a typical thermometer. So wet bulb is used as an indicator of the amount of moisture that's in the air. And how we get the term wet bulb is, what you do is you take a thermometer like this, and you add what's called a wet wick or a wet sock to the bulb. Now, what happens is the water in that wick or sock will evaporate depending on the amount of moisture that's in the air. So if you had a wet sock on this bulb and the air was extremely dry, a lot of moisture would evaporate. This is my symbol for evaporation. And when water evaporates off of here, what happens to the temperature? What happens to the bulb? It cools because the evaporation causes a cooling effect. So wet bulb would be cooler than the dry bulb. Now, you can imagine if the air is very humid, not much moisture is going to come off of the bulb, and it's going to not be much lower than the dry bulb of the room, okay? So that's where the term wet bulb comes in. You actually have a wet sock on the bulb. The drier the air, the more evaporation, the more cooling, the lower the wet bulb. So the wet bulb temperature is an indicator of the amount of moisture in the air. Dry bulb is just the temperature of the air, okay? So in my office here, 73-ish degrees, dry bulb. And let's see what the wet bulb is. Wet bulb's always lower than the dry bulb. The wet bulb is about 62. Okay, so pretty good conditions in here. It's about 54% RH, 72 degrees, so very nice office conditions. So 62.6 is the wet bulb. Now, I'm going to show you a demonstration of increasing the wet bulb. So I've got this hot plate, which I want to be careful of not to spill live on YouTube here. And you can see it's got this, I'll do this, okay? It's a hot plate. So it says the plate is 192 degrees. I'm not sure, I believe it's that hot. But anyway, the wet bulb in this office is about 62. So let's see what happens to the wet bulb temperature when I put it over this heated water. Okay. So you can see it's going up. It's upside down, but I'll turn it over here in a second. So you can see the humidity or the water in the air is affecting the wet bulb temperature, which is now 70 degrees wet bulb. Okay, it was 62, 63, now it's 70 degrees wet bulb. So that's just a little visual example of wet bulb temperature. Okay, so that's enough about wet bulb versus dry bulb. Now, let's talk about dew point. And then we're going to talk about, you know what, let's talk about, yeah, what the heck, we'll talk about dew point first. So dew point, the dew point of the air is the temperature at which water will condense. Okay, so the dew point in this office, I'm going to shake this because it got the humidity on it from our last example. The dew point is about 55 degrees dew point. So what does that mean? That means any surface temperature that's colder than dew point of 55, 56, 57, it's going up probably because it's reading my breath, is going to condense water. So the dew point is an indicator of when water will condense on the surface. So I've got an example to show you that. So the dew point in here is 57-ish, so any surface colder than that will condense water. And I've had this bowl of ice sitting here for a while, and you could imagine, this isn't a big mystery, but this surface temperature is going to be colder than the dew point of the air, right? The surface temperature here is about 37 degrees. So I don't know if you could see that or not, but you can see there's ample condensation here. It's actually dripping all over the desk. So the dew point in here is 55-ish, 57, I think. 55 right now is the dew point. The surface temperature here is 38, so you're condensing water on the surface. Okay? So that's what dew point is. The lower the dew point, the less moisture is in the air. That's how that works. So we'll go through another example of that. We'll look at that in a minute. Okay, so we talked about dry bulb, we talked about wet bulb, we talked about dew point. Now, relative humidity. This is one we get a lot of questions on and is still confusing to a lot of people in the industry. And if you're in the HVAC business, it's really important to understand the difference between humidity, which is grains per pound, and relative humidity. Okay, so relative humidity, we're going to demonstrate by using these beakers, okay? Let's say you had a volume of air, which is represented by this size beaker at 55 degrees. Let's say you heated that air up to 75. You would imagine the container of air would get larger. And you heated that up again to 95 degrees. Okay, so 95 degrees, 75 degrees, and 55 degrees. I should have found a way to put all these up here at once. Maybe I'll do that next time. But so what would, in this container, 50% relative humidity look like? Well, it's very simple. We take some water and we fill it up halfway. Yeah, it's probably a little more than half, but you know, we're not building the space shuttle here. Okay, so this represents 50%. It's driving me crazy. The engineer in me's got to get it right. Okay, so this represents 50% relative humidity at 55 degrees. Okay, so we'll put this aside here. So what would 50% relative humidity look like at 75 degrees? Well, we would do the same thing. We would fill it up halfway. I think that's pretty close. So this would represent relative humidity of 50% with an air volume at 75-ish degrees, okay? So here's the thing about relative humidity. What do you notice about these two quantities of water? Well, there's a lot more water in this container than there is in this one. But they're both 50% relative humidity. So the point here is relative humidity is relative to the temperature of the air. Okay, so at 75 degrees, 50%, there's a lot more moisture in the air than at 55 degrees, 50% relative humidity. Okay, so that's kind of the problem when you're using relative humidity to figure out how humid it is outside. let's take it to another extreme. Here's 95-degree container. We'll put 50% relative humidity in here. For some reason, I keep going just a bit over. So force them down. Okay. So at 95 degrees, this would represent 50% relative humidity. So again, two extreme examples. Both of these are 55% RH, relative humidity, but you can see there's a vast amount, a much larger amount of moisture in the air here than there is here. So, you know, like I came from Florida and I live in North Carolina now, but we had a lot of days that were extremely hot and humid, but the relative humidity wasn't that high because we were at 95, 78 wet bulb or something along those lines. But the relative humidity was not a good indicator about how much moisture is in there. So that's kind of the point here with relative humidity versus dew point. And again, the dew point is a much better indicator of the moisture in the air, okay? And we could show that on the psychrometric chart, and you could look at we have a lot of longer videos on our YouTube channel that talk about, you know, relative humidity versus dew point versus humidity. So that reminds me, we didn't talk about humidity. So humidity is different than relative humidity. Humidity is the grains of moisture in the air per pound of dry air. And a grain is a weight. I think it's 7,000 grains per pound. I have to look that up. Should have looked that up beforehand, but it's something along those lines. So grains are commonly used like to measure ammunition and to measure really small quantities, okay? So the moisture in this air, if you were to pour this out into another beaker, this would be the grains of moisture in that air. It's the physical amount of moisture in the air, okay? So that's the difference between humidity and relative humidity. And to illustrate that, again, the relative humidity of these two containers is the same, but you can see the grains or the physical amount of water in the air is much larger here for this one here. So that's a little bit about grains versus, or I should say humidity versus relative humidity. And here's another illustration of that. So right now in my office, I'm going to use this here. It's 69 degrees and 51% RH. 69 degrees and 51% RH in our office. Outside, it's 80% RH and 60 degrees. So if I look at my psych chart, this is called a psychrometric chart. If you're not familiar with this, we do have a lot of videos, again, on our YouTube channel to look that up. So if I look at the dew point in our office here at 70 degrees, 50% RH, it is about 50, make sure I get this right. I'd say 52 dew point according to the psychrometric chart, and this, you know, not extremely accurate temperature reading, but for the points of this argument. So 52% dew point. Now outside, it's rainy. It's 79 degrees, 59 degrees, and 79% RH. So 59 degrees, let's say 60 to make it easy, and 79% RH. I'd say it's about 54 dew points. So the dew points are almost exactly the same inside and outside, but look at the relative humidity. 80%, 79% versus 54%, right? So that's a good illustration of why relative humidity is not really a super good indicator of the amount of moisture in the air. You know, it's relative to the temperature, right? So the dew point of these two conditions is very close, within a couple degrees. You know, it feels nice in here. It's warm. it's dry and it's cool and wet, cool and rainy outside. But so the point is the relative humidity is not a great indicator of that. And if you've been around a while, you've definitely experienced that. So, okay, so one more thing I want to talk about here, which is sensible heat versus latent heat while we got all this stuff out here. So sensible heat, I'm going to try and bring this up again without spilling it. Sensible heat has to do with the heat coming off a heater, a light bulb. There's a light up here. There's a light back here. This hot plate has heat coming off of it. It's rather hot, actually. This cup has heat. It's warm to the touch. That is what we call sensible heat. It is independent of the moisture in the air. Okay, so sensible heat has nothing to do with the moisture in the air. I got a question here. Can you clarify with 70 instead with a small cup? Yeah, I'll get to that in just a second here. Let me stay on this this track of sensible versus latent heat. So sensible heat is just the heat coming off a heater, a light, etc. The temperature it says on here is 193. I'm not sure it's really that hot. If I zap it with this zapper, no, maybe it is that hot. I don't know, 190 something. So 203 degrees. So that's the sensible heat only. Now, if we remember, we looked at this cup of coffee earlier. So latent heat has to do with the moisture in the air. Technically, it's the amount of energy needed to change the state of water or a liquid, maybe even a gas too. So that's what latent heat is, okay? So the latent heat has to do with the moisture coming off of the hot coffee in this cup. Okay, so that's sensible heat, think dry. Latent heat, think, think wet, think moisture. So latent heat examples would be if you had a fountain, water fountain in your occupied building, that would be putting off latent heat. People put off latent heat. The average person puts off 250 BTUs of sensible and 250 BTUs per hour of latent because we have moisture and perspiration coming off of our bodies. Coffee maker, coffee cups put off latent heat. If you had an indoor pool, you would have a ton of latent heat. This beaker we have here is evaporating water, puts off latent heat, etc. So that's a little bit about latent heat versus sensible heat. So somebody asked a question about, can you clarify with the 75 degrees, 50% instead of with in a small cup? I'm not sure I understand the question, but I'll just go through this again. So we were talking about relative humidity, and these different beakers represent different volumes of air. So you could imagine, grab my 55 degree. So 55 degree volume of air, if you heated that up, it would be a bigger volume of air. To represent relative humidity, at these conditions, we're filling them up halfway to represent 50% relative humidity, right? So this is 50% relative humidity. The purpose of this demonstration or illustration is to show that they both have the same value, 50% relative humidity, but the amount of water in this beaker is much more than this one, okay? So that's kind of to understand. So the relative humidity is relative to the temperature of the air. So 50%, if this was 100% saturated, we would fill it all the way up with water, and this would be a 100% saturated condition, right? See that? Here's a good example too. So if you take this beaker of 95 degree air with the volume and you cooled this down immediately to 75 degrees, all the moisture would do what? It would overflow. It'd be 100% saturated. I'm not going to pour the rest of it in there because I don't want to make a mess, but you get what I'm saying, right? Like if you were to cool this down to this temperature, it couldn't hold anymore and it would overflow into the atmosphere. That's how you get fog. That's how you get, condensation on your cooling coil, etc. So that's kind of how that rolls. And for those who missed the dew point explanation, I'm going to go through that one more time here. So the dew point is 55 degrees. Okay. 56. Whenever I put it in front of my mouth, the breath makes it increase a little bit. It's a little sensitive with that. So what the dew point indicates is that anything colder than that is going to condense water. So any surface colder than the dew point in this office right now is going to condense water. And we have this example of, you know, this big bowl of ice cooling my Waterloo, which I'm about to drink here in a minute. The surface temperature of this bowl, as you could imagine, is colder than the dew point of the air. So the surface temperature here is 37-ish degrees. See if I could put that over here. Okay. And as you could imagine, we're getting condensation all over the place. It's actually dripping all over my desk. So that's dew point versus relative. Well, that's dew point. We already talked about relative humidity. Okay. So we hope you found this helpful. Check out our YouTube channel at HVAC-TV. And I've enjoyed this live show. I hope we brought some value to some folks. Our mission with HVAC-TV is to educate and empower the HVAC community. So we thank you so much for watching, and we hope to catch you on the next one.